Hello, everybody. It's my great pleasure here to present our work on accelerating the OP floor proof using the latest Ethereum upgrade, EIP-4844. So, next. Oops, it's not working. Next. Okay, cool. Yeah. So first of all, a quick intro of myself. I've been working in the Web3 area since 2018. Before that, I was a software engineer at Facebook, Google. Got a PhD, primarily working in the infrastructure. So my primary interest is in Ethereum data availability and layer 2 technologies. Get some support from both OP and also Ethereum Foundation. For example, Vitalik personal grants on cross-layer 2 bridge, data availability sampling, and ETH storage. And so for today's talk, it's also sponsored by the OP grant. Okay, so here's the outline. I will first give a quick intro about what is optimist rollup and its corresponding bisect dispute floor proof game. And then I will introduce our proposed multi-section floor dispute game, how we are able to accelerate the whole procedure to 1 to the 10 time. And then lastly, I'll give a summary. So optimistic rollup is one of the basically most popular rollup these days, including, for example, famous OP Stack and Arbitrum. The basic idea is that we can perform a lot of off-chain computation, which is very efficient with a very high TPS or very large memory model. And then we using on-chain some smart contract to verify the off-chain execution. For example, we can use in the ZK snark proof to verify the validity of the transaction results. Or we can also use in the floor proof to prove that the execution result of the off-chain is wrong. So how it works, basically there's a proposer defender that submit the claim, which is the execution result of the off-chain. And then this is a subjective claim that the proposer believes this is correct. And so anyone is able to challenge the claim within called challenge window. And when the challenging happens, there will be, we call dispute fault game, fault dispute game, which will basically interactively tells which instructions in the off-chain execution is wrong. And then once this execution is found, we can basically submit on-chain verification to tell that the challenge wins the game within this time window. And if no one is able to challenge the claim with the time window, then we will believe that, actually the smart contract will believe that this is assumed to be correct. So this is basic mechanism of the optimistic rollup. So optimistic rollup has a lot of benefits versus, for example, ZK rollups. First, it's much simpler to implement, and also to implement is prover. For example, in the ZK rollup, the major cost is the prover cost, which takes a lot of time, first to implement correctly, and second to prove the off-chain execution. So for optimistic rollup, that will be much simpler. And second, but things like the major disadvantages of optimistic rollup is that it requires a very long settlement time. For example, in the current optimistic like OP Stack floor proof, it requires 33 moves in the fault dispute game, and which right now is generally requires 7 days, especially consider some attack vectors. And also takes about 80 million gas, which costs about 0.3 Ether at about 20 Ether jury price. So the question is that can we reduce the moves to much smaller ones, for example, less than 10 interactions? And also we are able to reduce the gas cost to less than 1 to the 10. So that's basically the idea of why we proposed the multi-session floor proof. So before we dive into the details, I will give some quick overview of what the current foolproof dispute game happens. So first of all, we have a state which represents the current state of the virtual machine. For example, in the Fibonacci case, we will have the two last variables of the Fibonacci sequence. And in the more complicated cases, for example, specific instruction set architecture like MIPS, Watson, then it will contain a list of like registers, memory, stack. And we also have a state transition function, which tells that after running this state, what is the next state looks like. For example, in the Fibonacci sequence, then we basically sum these last two variables in the sequence, and then move the last one to the previous variable so that we can have a new state, which is BI, and then AI plus BI. And in the virtual machine cases, that will be a one-step execution of the MIPS OP code. Here I list all the OP code that is defined in the MIPS spec. And so in order to execute a large number of transactions, in general, we will have a multi-step state transition function, which just repeatedly apply the state transition function on the state with m times, so that we will have execution chase for starting from the initial called pre-state and the post-state of S plus I plus M. So here is an example of a Fibonacci example that when we start with the initial state with two variables is starting with 1, 1. And after 16 execution, then we will end with a result with 1,597 and 2,584. And we also have the corresponding execution chase of repeatedly running this Fibonacci sequence for 16 times. So the question is how we are able to make sure this S16 is correct, especially if somebody is wrong, then we can find out which step of this execution is wrong, and then we can use an on-chain verifier to challenge the corresponding execution and to tell that there's something wrong that is made by the proposer. So first of all, before we basically start a game, we need to know what is the claim. If the claim is very similar to a multi-step state transition function, but just tells that after running some pre-state with m steps, we get a corresponding post-state, and a claim can say that, hey, this is the post-state that we would expect it to return from the state transition function, or it can also claim that this is not the case, which is not the corresponding post-state that we given this claim. So in the Fibonacci examples, basically we want to, using the dispute foolproof, to tell that given this objective execution result, given the initial state and the corresponding post-state, and we want to basically have this, for example, this claim is given tells that this is a valid claim because the execution result is the same as the state transition function, but it's also, for example, suppose there's a proposer propose a claim with a wrong result, and this claim will become invalid, and that is the for dispute game trying to convince to the smart contract that something is wrong by the proposer. So what is the for dispute game? It's basically doing that given an initial state that is generally an off-chain, for example, block transition, so that we have an initial state of the world state of the layer 2 virtual machine, and then given a state function, for example, in the EVM case, that will be the EVM virtual machine, and then where both the defender and challenger agree how these two that is written on a smart contract, and we want to design an interactive game to prove on-chain that suppose there's an invalid claim that is of a long off-chain execution, For example, running a very, very long sequence of Fibonacci result, and that is really wrong by the on-chain smart contract. And in these cases, this M, which is the off-chain execution number of steps, can be super, super long. For example, in the optimistic OP stack cases, this number of steps can be 2 to the power of 73. That basically covers most of the layer 2 transitions with a large number of, for example, blocks. And another thing is that the one-step state transition function is able to be verified, run on top of a blockchain, so that we can verify any one-step transition is correct or not. And so this is, for example, in the OP stack, it provides MIPS.SOL, so that we can verify a one-step MIPS OP code execution that on top of blockchain. So now the game becomes that the defender agrees that I have a proposed root claim that starting from an initial state with some execution steps, off-chain execution steps, and we get a corresponding execution results, while the challenger says, hey, this something is wrong, and I would like to challenge in how you execute this data and what are the intermediate state during this execution. And then FDG will be able to run as a smart contract on chain to determine who is the winner. So for Fibonacci cases, it's basically we want to prove that suppose a claim is wrong, like objective is wrong, then we can use in this game to prove that it's actually wrong on a smart contract. But we cannot prove that if the claim originally is valid, then we can prove that it's incorrect, or we cannot prove any claim that is correct. So this is basically the capabilities of the FOP distributed game. Basically, we just suppose the claim is invalid, and we would like to use in this game to find something is wrong. And so the optimistic assumption is that suppose there's nobody is able to challenge the root claim for a specific time window, then the protocol assumes that the root claim is valid, which means that the finality window, which means that nobody challenged the game, must be greater than the minimum challenge window, which right now requires 73 interactions of the on-chain transactions. And in general, it takes about 7 days. Why is such a long time? The founder of OpenStack, Kevin, gave a really good thought about how this can happen. And one key factor is that it highly depends on the number of the interactions, or we call FDG moves, between the smart contract and also the defender and the challenger. So in order to basically to play this game, so one party, for example, right now this is defender, will first, if it disagree with this result, it will basically submit a list of subclaims. In the bisect case, section cases, there will be 2 subclaims to divide these two, the whole root claim into 2 subclaims, which counter corresponding original claim, saying that, hey, I disagree with your claim, and this is my intermediate execution result, and tell me which one you disagree. And so this requires the counter subclaim contains the new state, the intermediate states, which must be data available, and the rest of the state is already exists on the chain, so they don't require this additional information. And at the same time, each subclaim halves the original claim's number of steps, so that we would like to reduce this step to 1, so that we are able to finally decide who is the winner using the on-chain verifier. So the defender must respond that I either disagree with the first part of the execution, or the second part, or agree with the first part of execution but disagree with the second part of the execution, or it may fail to respond within timeout, so that he will fail the game. And so suppose the defender agrees with the C2, that's the previous half section of the execution, but disagree with the second half, then it will counter the second half of the subclaims. And this repeatedly, and finally, it will reaching a state that both parties disagree, actually agree with the previous state, but disagree with the corresponding post state, and with only one step to execution. And when reaching this state, now we are able to settle the whole dispute procedure using the on-chain one-step verifier. So this is basically how the foolproof dispute game looks like. And here we can have the whole FDG claim tree, which will basically be able to find the corresponding counterclaims given a corresponding original claim. So basically this lists all the possible claims in the whole procedure. So for the bisect FDG, this requires log2m moves between the defender and the challenger. And suppose we want to support a lot of the off-chain executions, then it requires log2m moves, which m equals to 200, suppose 2 to the power of 73, that require 73 moves to determine which step is disagreed between the defender and the corresponding challenger, and then it can settle by the corresponding on-chain one-step verifier. And this takes a lot of the time and also gas costs. So one nature idea is that instead of split the whole execution trace into 2 segments, why not we are able to split this into multiple segments so that we just need to able to accelerate this procedure with much finer granularity in each move. So this is the basic idea of multi-section for dispute game. So for here give an example that we split the whole execution trace into 4 sections and then provide additional 3 states to tell that the corresponding execution result in the middle. And then the defender must respond to with 4 choices. Either it disagrees with the first quarter of the execution result, or the second quarter, or third quarter, or the last one. Or the defender may also fail to get the game by timeout. And so this will basically reduce this. We only need 2 moves so that we are able to find out which execution result is disagreed, the step disagreed between the challenger and also the defender. And so that we are able to greatly first reduce the number of claims in this tree. So for all these, for example, claims in, for example, in the 2 or 3 and all these layers, they will be removed because we basically using this each time it will create 4 counterproofs in the previous example. And at the same time, also reduce the number of interactions. So we require only 2 moves or interactions so that we are able to find which instructions is disagreed between these 2 parties. And this will be the claim tree of the multi-section for distributed game using k equals 4. So the good thing is like using multi-section foolproof, we are able to reduce the number of moves to log, from log to m to log to n, where n is the number of the sections. For example, if n is 4096, then we can reduce the number of moves to 7, from 73 to 7. And the coins is that since we need to carry more data to tell the corresponding intermediate states of the execution for each counter moves, increase the corresponding gas per move. For example, using n equals 4096, that will, suppose we put the corresponding intermediate execution trace using core data, that will need extra 2 million per gas in each move. That will be considerably larger versus the current bisect game. So the question is, can we reduce the gas while harvesting the benefit? The key idea here is now we are able to use an EIP-4844 blob, which is just launched about 2 months ago, which introduced a new object for binary large object, which can be able to carry 128 kilobytes of data. And now the key idea is that why not use this blob to carry 4,095 state hashes so that we can able to submit one transaction with one blob and be able to counter 4,096 subclaims. And in addition, thanks to the upgrades, the blob cost versus core data is, this is a huge number that is cheaper versus the core data, which means that corresponding actual gas can be almost negligible using the blob to carry those intermediate hashes of the subclaims. So here is the clause summary. Using the current n equals 2, it requires about more than 18 million gas with more than 73 moves. And we can, using the core data, to carry the corresponding intermediate states. For example, using n equals 256, we can reduce the number of gas to 3 million with about 9 moves. And we can further optimize this using the EIP-4844, so that we can reduce the move to 7 and further reduce the number of the total gas to 1 million, which is 10 times smaller than the original n equals 2. That is the current implementation of the OP stack. So currently we have a proposal that is submitted to the OP stack, which is already accepted. And we also have a specification to basically describe mathematically rigorously to how this multi-section flow proof works. And there's also Ethereum optimism discussions. So if you have any questions, feel free to share comments there. And we also open source the whole code so that if you have any ideas to contribute or test this feature, welcome to contribute to the repo. And so with all these features, now we are able to do a lot of crazy ideas. For example, we are able to prove a super large execution on off-chain. For example, artificial intelligence interference or training procedure using optimistic flow proof and be able to almost instantly settle the corresponding flow proof game if somebody is wrong. So we co-work with Aura to develop all this OPML so that we are able to employ the benefit of multi-section flow proof to accelerate this procedure. So many thanks for attending my today's talk. If you have any questions, feel free to reach out to me, and I'd love to see you there. Thank you very much.
Thank you so much. Thank you. Yes, it's working. Thank you. Are there any questions?
Yeah, any questions?
Hey, thank you for having me. So, and the question is, like, how do you envision, like, the future of, like, what you're building? Like, what you're trying to achieve, generally speaking, and what is the kind of end goal, which you can call a success, basically, in terms of development of the features, maybe, and so on. Thank you.
Yeah, so the question is, what's the future of these proposals, and how do you define the success metric? So basically, we are right now running this. The whole proposal is to be able to first implement all this feature, pass all the tests, and then and test this feature on a test net, and deploy OP stack, be able to do the flow proof. And actually, this is the current stage of BiStack OP stack flow proof. And next step is once they have been launched in the mainnet, we also launch the whole feature on top of mainnet, and then so that we are able to collect more detailed results. For example, how much gas is being saving, and all those like the number of time that is reduced. And this is the basic success metric. So we definitely, the ultimate goal is running on top of the mainnet. And there's another proposal that I will go into discuss tomorrow, is to using the ZK flow proof to also accelerate the final step, or maybe multiple steps, so that the ultimate goal will perhaps to reduce the interaction fraud proof to 1 or 2 times, so that it can reach almost instant settlement using the fraud proof while saving a lot of costs, both the OP fraud proof and also the ZK fraud proof itself. So we will discuss some ideas tomorrow about the ZK fraud proof there.
Thank you so much, Zhou. Working now? Yes.
Thank you.
Thank you so much, Zhou. I believe we are out of time. Thank you again. We're going to be getting ready for our next talk. Thank you.
Thank you.